Hi there and welcome to this video for Senior Physics on Light and Waves. This video we're going to explore Snell's Law. Now when we looked at our previous video on refractive index, we basically said that as light moves from one media to the next, the media changes density, and as a result the speed changes according to that density. Now the real problem is when we're dealing with light, we're dealing with an object or a substance which is moving incredibly quickly, 3 times 10 to the 8 meters per second. Now, measuring that in the laboratory is incredibly complicated, and we won't even go into the complexities behind how do you measure the speed of light. So we needed something that was going to allow us to do some basic measurements in the laboratory to determine what was going on with respect to the light, to be able to look at the refractive index, and then be able to work out what angle was going to come out, what the refractive ray angle was going to come out as. So we've got the scenario here where we've got two media, we've got light passing from one media into the next. The speed is changing. In this case, it's going to be slowing down. As you can see, the refractive ray is getting smaller, so media 2 must be a more dense object. Now, it was Willy Broad Snell, who was a Dutch mathematician, who basically came up with a law which allowed us to utilize mathematics to determine the angle of refraction of light passing through an object. Now, what I always find amazing is you look at the dates when these guys were around. A lot of the famous scientists and a lot of the laws that we look at in physics, these were looked at way before we had computers, we had high-tech technology. These guys just used the concept of observation and applying basic laws to those observations, coming up with mathematical equations and algorithms, which we still use today. And even now, it's that they're utilized, and so as a result, their thinking behind it was so good, they were able to produce materials which are accurate. So what did he come up with? Well, he basically came up with this formula. He said that the refractive index of the two objects basically would apply so that we would get the ratio between the sines of the incident ray and the refractive ray. So he came up with an algorithm of the refractive index of incidence light times the sine of the angle of incidence will equal the refractive index of the second media, which we're going to just call the refracted ray, times the sine of the refracted angle. So we get Ni sine I equals Nr sine R, where I is the angle of incidence and R is the angle of refraction with the sines. So the result is that if we're going from air, we know that Ni is going to be 1. So as a result, we get Nr, if I wanted to find that refractive index for the second medium, Nr would be made up of sine theta I divided by sine theta R. Okay, so as a result, this is the formula that we would get if we were going from air. So you can see that the refractive index of the second medium, R, will equal sine theta I divided by sine theta R as we're moving from one to the other. So let's look at a quick example. So here I've got two media. We've got light traveling from water going into glass. Now we know that glass is a lot more denser than water, hence the refracted ray is going to be bent towards the normal. So it's going to be less than the incident ray. Now you can see the incident ray is coming in at 20 degrees to the normal. So we're going to apply our formula to it. So let's write down what we know. We know that water has a refractive refractive index of 1.33. We had that from the table in our previous videos. We know that the refractive index of glass is 1.52. Now all of this data would be given to you in an exam, either in the table or in the question, or you may be expected to calculate it using the speed of light. And there will be information that would allow you to apply that speed of light calculation, n equals V air divided by V media, that would allow you to apply it to find the refractive index, which would then allow you to find the refractive angle. Now we know that our incident ray is coming in at 20 degrees to the normal. So I place all my information into my Snell's law equation. So remember, it's Ni sine theta I equals Nr sine theta R, where R is the media 2, I is media 1. So I'm just going to substitute the I's and the R's for the type of media that I'm dealing with. So I've got the refractive index of water, so this is that third line in that blue area, the refractive index of water, N water, times the sine theta I, which is the incident ray, equals the refractive index of glass, N glass, times the sine theta of the refracted ray, theta R. So substitute those values in. I get 1.33 times sine 20 degrees equals 1.52 times sine R. So when I take that 1.52 over, so I divide 1.33 times sine 20, all divided by 1.52, that will come up with a value of 0.299. I then need to, that gives me sine R, sine theta R. I now need to do the inverse sine of 0.299 to get the overall angle. So I've got to take the sine to the other side. Remember, sine is multiplying theta R, so I've got to divide it, so hence it's sine to the negative 1. So you'll do that second function sine on your calculator, 0.299, and I end up with the refractive angle being 17.4 degrees. Okay, so what I've done is, again, I've posted up a variety of different Snell's law problems and worked through them with you. What I suggest you do, have a good look at those videos, because I'm hoping that you'll see how that process can be used. I've tried to use a variety of different questions that you might find useful. Have a go through those questions and then use those skills and apply them to various scenarios that you'll get in class. Okay, well, I hope you found that useful, and I look forward to you joining me again. Thank you for watching.